In this video, I'd like to have a discussion regarding sound. Before we begin, let's have a look at the definition of sound here in this text. There is a definition of sound, or for sound, and here it is. Let me put everything here in view. And it says here, sound is a longitudinal mechanical wave which travels through an elastic medium. Well, let's look at these words here individually. Longitudinal mechanical wave. Down here is a picture of a tuning fork. A tuning fork acts as a source of longitudinal sound waves in air. And when the tuning fork is struck, it vibrates. And in its vibration going towards the lady here, it compresses the atoms in the air, causing this area here of compressed atoms. And when it goes the other way, it doesn't compress the atoms, so the atoms are a little more scattered, farther apart from each other. And this is a longitudinal wave. It's a compression wave. As the fork vibrates back and forth, compresses the atoms, and then it doesn't, and it does, and it doesn't, and wind up with this kind of a wave. And it has a direction, and it's longitudinally going towards the right. So sound is a longitudinal mechanical wave. Mechanical means something has to generate the sound, like this. There we go. Here is a bell. And inside here, there's a hammer, and of course we have this housing. So something has to generate the sound. This is called mechanical generation. Or if we have another piece of steel, here's a piece of steel, and here's another one. So I am making sound, mechanically making the sound. So something has to generate sound. So it's a longitudinal mechanical wave, which travels through an elastic medium. And let's have a look at this elastic medium. John Dalton, about 150 years ago, said that atoms behave like solid spheres. The key word is behaves like solid spheres. And here are some solid spheres to demonstrate elastic behavior. And according to John Dalton, who said that atoms can be modeled as a solid sphere, just like this. And if I put some energy to this ball right here, I'll take that one out, that energy is going to be transferred to the next one. Consider this to be an atom, and that is another atom. This atom is traveling, or it's being compressed by the tuning fork and being moved slightly that way. Here's what happens. Nope, not have to hit a little bit harder. And again, elastic means it's going to transfer its energy to that one, and in itself then it will stop because its energy has been transferred. If I can do that, there that's a little bit better. Slow down a little bit. So it has transferred its energy to the other atom in front of it. And if I put, say, 3 of these together, this one will strike that one, and in turn it will strike this one. And that one, because I have nothing here to holding it, is going to shoot off. This is called elastic medium or elastic energy. I'm going to go, and you can these two here should come to a stop. Obviously, it's not perfect. And let me just move these down here so I can keep them within the field of view. If I hit this hard enough, there we go. See, these ones stopped. The energy was transferred and up to that last one. So in here, this actual wave, it's not that these atoms here are traveling all the way to the other end. These atoms are striking the atoms next to it, striking the atoms next to it, striking the atoms next to it. They're basically stationary, staying here, but it's that transfer of energy that's causing this wave to travel from here all the way to there. It's not the atoms, not this atom here. Consider this the atom starting here and then traveling all the way to the person's ear. It is this elastic energy striking this atom, and this one striking another one, etc., all the way down. So sound is longitudinal mechanical wave. You need to strike things in order to make sound, which travels through an elastic medium. I'll put these away. There is a very famous experiment which is often cited, and here's a picture of it. We have that bell. Here's a bell. And you can hear the sound because the sound is traveling through the air. Air is made up of molecules. We have a bell inside of this, looks like a jar with a stopper on it. And this is an electric bell, so it's got some wires, here to batteries, or in modern day, we'll just plug it into the wall. And this bell here will continually ring, 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 ring inside of this jar. And the jar is connected to a vacuum pump. And as we take the air out of the jar, the sound becomes muffled and becomes less and less and less, till eventually there is no sound at all, but the bell is ringing. In order to have sound, you need to have a medium in order to transmit the sound. In a vacuum, if you take all the air out of here, there is no more molecules. There's no more interaction between atoms because they're not there. They've been taken out. There's no more elastic behavior between atoms. As a result, no sound. So sound requires a medium, whether it be air or a liquid or steel. Here's a chunk of steel. If I were to put my ear to that steel, put my ear here and strike it, I'd hear it all the way across. It would carry the sound. So sound requires a medium. It will not travel in a vacuum. Back to the definition. Sound is a longitudinal mechanical wave which travels through an elastic medium. Medium is air, liquid, or a solid. Now back to our problem. I'm just going to skip a few pages here. A couple of definitions, which I will leave here momentarily. And we're going to need to understand this one right here, the hearing threshold. I'm going to leave this definition here for hearing threshold. And pain threshold. This is for our ears. What we can hear, barely hear, and then begin to hear afterward. This is the minimum amount that we can hear. And this is the maximum amount that we can hear without feeling pain. And the equation I'm interested in right now is this one. So let's go back to that word problem. Here it is. And it says here, now what I'm really doing here is I'm going to develop an equation. Not so much use this in order to solve something, but more to develop an equation. The equation I showed you earlier, I'm going to call it, on the left-hand side, sound level. SL is equal to log base 10 of intensity 1 divided by intensity 2. It says here two sounds have intensities of 0.25 watts per square meter, and the other one has an intensity of 10 watts per square meter. Compute the difference in intensity levels in bells. Okay. So I've renamed the equation slightly. Here's the equation. Starts with the letter B for bells and the log of I1 over I2. So I've changed it slightly. We call this sound level is equal to the log base 10 I1 over I2. Let I1 be, we'll make it the large number on top and the small number on the bottom. I1, we'll call it 10 watts per square meter. And I2, 0.25 watts per square meter. Again, my intent here is to develop an equation, not so much to do all this math, but to develop this final equation. Now let's put these numbers into this equation. The sound level is equal to log base 10. And I chose that I1 to be 10 divided by 0.25 watts per meter squared. Looking at the units, watts per meter squared on the top and watts per meter squared in the denominator, they'll cancel out. And doing the math, 10 divided by 0.25, or I'll just go ahead and write that down. The sound level is equal to log base 10 of 10 divided by 0.25. In brackets, this is a fraction. And you will note here that the units have canceled out, so there are no units. This is that unitless number. Doing this in our calculator, let's do that. And clear that. So log base 10. I go log, and it's already understood. It's going to be a base 10. Open that bracket. 10 divided by 0.25. This is the argument of the logarithm. It's a fraction. 10 divided by 0.25. Close that bracket. If I ever put it the other way around, I'll just get a negative number. Same number, but it'll be negative. So in order to keep it positive, I chose to put the large number in the numerator and the smaller number in the denominator. But that's just so it stays positive. Is equal to, and I see 1.602, I'll write that down, is equal to 1.6020599. Now the question is, what am I going to use for units? They canceled out. It has been decided by definition, that the unit for this sound level is going to be a bell. And this bell, this is named after Alexander Graham Bell. And the unit, well, they dropped an L. And I'm going to keep the capital letter for B. So sound level has the units of bells by definition. Even though this is a dimensionless number, we're going to call it bell. So I'm going to put it over here on the left-hand side. Sound level in bells is equal to 1.6. To turn this into proper significant figures, I'll have to look at the measurements. What measurements were given to me here? So this must have been a measurement. Somebody must have taken some meter and made this measurement of intensity and made this measurement intensity as well. Two significant figures here, two significant figures here. So I'm going to change this to two significant figures. So the sound level is 1.6 bells. B. Now bell is a large value. It's a large unit. Bell. A bell is a large unit. Consider the meter stick. Consider the meter. Here is a meter. And it says here, 10 millimeters is a centimeter, and 100 centimeters is equal to 1 meter. So this is a meter stick. At one end of the meter stick is the 0. Right here, 0. And then we have 5 centimeters, 10 centimeters, etc. going along the length of the meter stick. All the way to the other end is 1 meter. And you can see that this 1 meter also has smaller graduations. Sometimes you don't want to use the whole meter in order to measure something. You want to use smaller graduations to measure the length of something. So let's have a look at that meter. consider this. I'm going to represent the meter here. At the 0, and over here I'm going to call this 1 meter. That distance, call this 1 meter. We'll take this distance here of 1 meter, this meter stick that I have here, and let's divide it into 10 even units. Divide that length into 10 even units. And we'll start here. That's about 5, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Divide it into 10 even units. The length of each one of these units now, with reference to the meter, since there are 10 of them, it'll be the length from here to there is 1/10 of a meter. 1/10 of a meter. That will be this length. That length here would also be 1/10 of a meter, and so is this one. And 10 of these then would add up to 1 meter. If I were to divide this 1/10 of a meter into 10 even spaces again, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and do the same for each one of these. So there's 10, 20, 30, 40, 50, 60, 70, 80, 90, 100 even little spaces that make up this meter. That'll be 1 divided by 100 of a meter. Each one of these segments then will be 1/100th of a meter. And if I were to take each one of these little segments, 1/100th of a meter, and divide it into 10 little spaces again, 10, 10, 10, all the way across, that will give me 1,000 lines. 1,000 of a meter. So each segment then will be 1,000th of 1 meter. And these have names, 1/10, 1/100, and 1/1000. They have names, they're prefixes. And I'll show them to you. And here they are. Centimeter, or the centi, is 1/100th. I mean 1/10 is centi. Excuse me. 1/10 of a meter is a deci, or a decimeter. 1/100th is a centi, or a centimeter, and 1/1000 is a milli, or a millimeter. So this has a name, centi, meter. And this one, 1/100th. Nope, my error. This one is decimeter. See, this one here is centimeter. And this last one here would be milli. 1/1000th of a meter, 1/100th. And this is the one I'm interested in. 1/10 of a meter is a decimeter. Now let's take the bell and do the same thing. Consider this being 0 bells, and all the way over here is 1 bell. Let's divide this into 10 even segments. 1, 2, 3, 4, 5. Well, not likely even. 1, 2, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 even segments. Same as here. The strength there, the length of each one of these segments is 1/10 of a bell. And 1/10 has a name, deci. So this is decibel, properly pronounced decibel. And I'm going to take the capital letter and make it the lowercase. So the unit of sound, the most commonly used, is the decibel, which is 1/10 of a bell. Technically, this is correct, but what is used in everyday language for measuring sound loudness or intensity is the decibel. And it comes from this, dividing the bell into 10 even spaces. So we have the decibel. And let's change this one into decibels. I'm going to flip the page over and I'm going to put this on the top. And I want to change bells, 1.6 bells, into units of decibels. I'm going to flip this over. And prior it says I had 1.6 bell. By definition, we just did that, is 10 decibels, dB, is equal to 1 bell. We did that earlier. A decibel has the units, the shortened units of dB, decibel. And it takes 10 decibels to equal 1 bell. That's what I have here. So 10 decibels is equal to 1 bell. I want to convert this into decibels using this conversion factor. So 1.6 bell times, and rearranging this into a fraction, we're going to put bells in the denominator. Ten decibels is to 1 bell. Bell and bell cancel out. So we'll take in the 10 times the 1.6, and that comes 16. 10 times 1.6 is 16 decibels. So 1.6 bells is the same as saying 16 decibels. If I were to do this over and over and over again, find the solution in terms of bell, and then converting it into decibels, I find that I have to multiply each one of these times 10. Every time I do a solution using this equation, the value, the units will be in bells. And then I have to change bells into decibels. I have to multiply this by 10 each time, according to what I have done here. So instead of doing this conversion, let's put that number into the equation itself. So modifying the equation I showed you earlier, sound level is equal to, this is the conversion factor, the multiplication of 10, log base 10 of the original equation, I1 over I2. And what I have here, and all this was all to do nothing more than to derive this equation right here, so you understand where the 10 comes from. And this is the general equation for sound level. And it will have the units of decibels, dB, or decibels.